Astronomers have been observing the cold dust cores in the central zone of our Milky Way galaxy. The Milky Way's central molecular zone spans the innermost 1600 light years of the galaxy. In comparison, the Sun is 26,600 light years away from the galactic center and includes a vast complex of molecular clouds containing approximately 60 million solar masses of molecular gas. The gas in these clouds exists under more extreme physical conditions than elsewhere in the galaxy on average, with higher densities and temperatures, more intense pressures, magnetic fields, and turbulence, along with higher cosmic ray abundances and ultraviolet and X-ray radiation. The central molecular zone is therefore a unique laboratory for researching star formation. Not only are these conditions rarely observed in the rest of the Milky Way galaxy, they appear to be similar to the conditions in extremely luminous star-forming galaxies in the early universe, and offer an indirect glimpse into understanding the cosmic history of star formation and development, not otherwise currently possible. However, it is a conundrum. The star formation rate in the central molecular zone is much less than would be expected. It is barely 1/10 of a solar mass each year. The origins of stars are understood to be the densest regions in giant molecular clouds called clumps, whose characteristic sizes are 1 to 10 light years. These clumps fragment further into gravitationally bound cores, whose characteristic sizes are about 10 times smaller. Individual stellar systems can then form from the cores. The nature of the transitions between these evolutionary stages requires large surveys of both star-forming and non-star-forming structures across a hierarchical continuum of relevant scales and physical conditions. Astronomers have released the new survey data. It is a complete and unbiased map of the high-density gas in the region. High-density regions are quantified by the amount of molecular hydrogen gas along their lines of sight and are characterized by having so much dust that the visible light is completely blocked. The survey was as a result of a large 550-hour sub-millimeter array program and resulted in new catalogs of the compact cores in the region of the Milky Way galaxy. There are currently 285 separate cores that were unambiguously discovered. Another 531 have more tentative identifications. The cores in the central molecular zone are elsewhere, are potential sites for future star clusters, but bright foreground and background emission towards galactic center makes it quite difficult to determine these cores' masses precisely, leaving this critical predictor of star formation highly uncertain. It should be noted that the emission is also one of the reasons for the catalog being so challenging to prepare. The astronomers were nevertheless able to estimate the maximum star formation potential of the cores in their catalog by making generalizations along with realistic assumptions about the core's masses, temperatures, and other properties. They found a maximum potential star formation rate of between 0.08 to 2.2 solar masses per year, perhaps even as much as the current average star formation rate in the entire galaxy. The result highlights the puzzling weakness of current star formation in the central molecular zone. The research, which was done to ensure that they had a catalog of all the cores for further research, is a further step towards understanding star formation in the extreme environments present in the central molecular zone and the early universe. Stars are born in dense clouds of molecular hydrogen gas that permeates interstellar space of most galaxies. While the physics of star development is quite complex, recent years have seen substantial progress towards understanding how stars form in a galactic environment. What ultimately determines the level of star formation in galaxies, however, remains an open question. Two main factors influence the star formation activity: the amount of molecular gas that is present in galaxies and the time scale over which the gas reservoir is depleted by converting it into stars. While the gas mass of galaxies is regulated by a competition between gas inflows, outflows, and consumption, the physics of the gas-to-star conversion is currently not well understood. Given its potential to form a critical role, many efforts have been undertaken to determine the gas depletion timescale observationally. However, these efforts resulted in conflicting findings, partly because of the challenge in measuring gas masses reliably given current detection limits. Like, comment, share, and subscribe. Let me know what you think about this fascinating look at the cold dust cores that exist in the central molecular zone of our Milky Way galaxy, and the potential for greater star formation in these regions. Well, of course, we are forever anticipating new information coming from astronomy and space observations. Of course, remember to leave your comments down below. Be safe. Keep your eyes focused on the stars. Enjoy the sky out there. Take a moment and breathe and look at the beautiful stars, and take a look at the moon if you can. Of course, have a wonderful evening and potentially intriguing night under the stars. Enjoy the view out there. Take care and goodbye.